Welcome to Lecture 17 for Chemistry 312 Radiochemistry. This is the lecture on radiochemical separations, and this is the second part of the 4 parts of Lecture 17. The readings for Part 2 are the same as all the other parts: actinide separation, science, and technology. In Part 1, we covered solvent extraction. And in Part 2, we're going to explore ion exchange and volatility-based separations. Ion exchange, I'm sure you're familiar with. You'll see that it's a very robust field. There are numerous separations. We're not going to touch on them all, but we'll see that you can achieve separations by varying oxidation state and by also varying the acid solution or the solution itself. There are separations that involve the use of alcohols or the addition of ligands to the solution to remove certain metal ions from the ion exchange resin. The other separations that we'll cover in Part 2 cover volatility separations. And in this case, for the nuclear fuel cycle, there are examples of volatility-based separations, but overall, volatility-based separations are not as robust as the ion exchange-based separations. Continuing with the theme of separations, we now move on to ion exchange and chromatography based separations. Unlike solvent extraction systems, where both parts of the separation system are dissolved, you can think of an ion exchange or chromatography system with a solid exchanger and a dissolved sample. The sample dissolution route can be very similar to what we discussed in solvent extraction. And the solid exchanger can actually utilize the same ligands that we also explored in the separations by solvent extraction, except that these ligands can be sorbed or covalently bonded to a solid phase. Separation is achieved by adjustment of the solution matrix. This is based upon the chemistry of the column. In other words, we could have a cation or anion exchanger, and the solution of the elements that we're interested in separating, including the target element itself. Generally, what occurs is that we have retention of a target radionuclide on a column. The other elements can be removed, and then the purified target radionuclide can be removed from the column. It is also possible to sorb all the other elements that you're not interested in onto a column and allow your target radionuclide to flow through. But this is often not done, as you have chances of having the non-target, non-specific radionuclides come through along with your target. The solutions can be adjusted, as just as we talked with the solvent extraction system, where we had systems where we could extract into an organic phase based upon acid concentration. With our solid ion exchange and chromatography separations, the acid concentration can be varied, the counter ion can be varied. For instance, a nitrate ion can be varied by the addition of sodium nitrate, in addition to using nitric acid. And similar to what we discussed with solvent extraction, a redox agent can be added to change the oxidation state of your target radionuclide and changing its behavior on the column. Often you elute your target radionuclide from a different condition than the initial addition of the radionuclide under the target. Again, this condition can either be the change of the redox state of that radionuclide or a variation of the acid concentration. You can include an addition of an isotopic tracer to determine yield. In other words, an isotope that differs from the same element, different isotope than the one that you are performing the separation on. And the chemical behavior of your metal ion on the column is measured by distribution. And you can think of this as very similar to the distribution coefficient. But what one could evaluate in a column system is you could either look at the column volumes that are needed to elute the metal ion, or if you did a distribution, you could talk about grams of material or some unit mass of material per unit volume of solution. Some of the fundamental properties of resins are listed here. The resins themselves can be organic or inorganic in structure. They can be used to exchange cations or anions from a solution phase, or even neutral molecules such as XAD resins. There's a generalization in their structure. They usually have some sort of backbone that's not involved in bonding, and a functional group which involves the complexation of the cation or anion that is involved in the exchange process and separation process. Some of the properties of resins that can be evaluated are capacity. In other words, the amount of exchangeable ions per unit mass of material. One route of doing this with a cation exchanger is measuring the proton exchange capacity. This is the number of protons, or the concentration of protons, as a function of unit mass of the material. And a proton exchange capacity is often measured in something such as milliequivalents per gram. You can also discuss some other properties of the resins, such as selectivity. A broad one is cation or anions. Obviously, cations are exchanging cations positive ions, and the anions are exchanging negative ions. And there could also be some selectivity within anions and cations for a given resin, and these distributions generally vary with acid concentration. Therefore, that's why acid concentrations are one of the parameters which are changed in order to achieve selectivity by ion exchange. Organic resins have some basic components: backbone, functional group, and these work together to apply for structure of the material. The backbone is often supplied by a cross-linking polymer chain. For instance, this linkage group shown here. Sulfur linkage groups can also be used. These cross-link different parts of the material, and they can limit swelling. They can restrict cavity size of your resin material, changing some of the properties and flow of solutions through these polymers in an ion exchange column. You can also functionalize groups. As an example here, there are two primary functional groups, both cation and anion exchangers, shown here. This is a protonated, so proton form, chlorine form. For resins, you will often see if they're protonated or cationic. They can be protonated, they can be a sodium form, potassium form. Same thing with the anionic. They can be chlorinated, nitrates, other anions. These are often described on the resin materials. Now, because of the cross-linkage and the random nature of that, you also get randomness in the structures of the resin material. So there's a range of distances between sites, and some of the environments, the localized environments, can vary a bit within the resin material. So you can have some near organic backbone, or mainly interacting with solution. So metal ions can be close inside the resin material, harder to exchange, or farther away, closer to the solution phase, so somewhat easier to exchange. This can influence some of the properties of the resin, and it's often linked to this cross-linkage behavior, whether and how much pore size and capacity the resin material will have for solution. There is another organic resin, which is absorption-based resin. One can have a resin material which is composed of long-chain carbons on an organic backbone. Example, these are XAD resins, and in these cases you would exchange organic material. So these type of resins just absorb organics from aqueous solutions. So one could imagine if you would have had a solution where you bound up with a large organic molecule with a relatively long carbon chain, that could sorb to a resin. For example, humic acids, which are organic matter in groundwater, dissolved natural organic matter in groundwater. When they sorb metal ions and you run that through an XAD resin, you can sorb the metal ion onto the XAD resin. And also, these XAD resins, you can sorb other molecules to them, organic molecules, so you can wind up functionalizing the XAD resin and make those into functionalized exchangers. Inorganic ion exchangers can also perform separation functions. One of the main differences between the inorganic and organic resins is that the inorganic resins tend to have more formalized structures, there's less disorder, so these may be more useful in performing size separations. Examples of some materials can be silicates, alumina type structures. Both these structures are tetrahedral. They can be combined into extended structures such as that are shown here. These aluminosilicates, an example of aluminosilicates that can be used in separations include zeolites, clay minerals. These are often cation exchangers where metal ions can fit into these cavities and they can be synthesized. An example of an inorganic resin material that is relatively straightforward to synthesize are zirconium phosphates with a structure shown here. If you just take a metal salt with a phosphate solution, you can have a precipitate which forms, which has a fairly regular structure, and if you can imagine, you can tune the gap between the metal ions and with this bridging oxygen by choosing the metal ion itself. These precipitates can be prepared, size separated, and then a material like this would be very good for separating tetravalent metal ions. The zirconium can be replaced by other tetravalent metal ions to vary the gap so that you can have some tunability in the size separation in addition to the oxidation states. Another example of an inorganic resin, as was mentioned above, are zeolites. These are often microporous aluminosilicate materials, and they are used as sorbents. An important consideration in ion exchange is the reaction kinetics and the exchange kinetics that takes place during separations. These kinetics are often diffusion controlled. You can have film diffusion, so on the surface of a resin, or particle diffusion, movement into the resin. One can imagine that this diffusion is going to be varied with different flow rates, so that's also an important parameter in assessing kinetics and reaction times on a column. Generally speaking, kinetics tend to be fast, or faster systems are preferred since separations are easier to achieve. Also, general trends is that an increase in cross-linking tends to decrease the kinetics. Systems that are cross-linked, the exchange sites are often hard to access, so overall systems slow down. One way of evaluating extraction is with theoretical plates. Theoretical plates fundamentally break a column down into how many zones of reactions are occurring on a given plate. Swelling is also an important process in kinetics. Solvation can increase swelling, and this can also greatly increase exchange. However, greater swelling also tends to decrease selectivity since cavity sizes are no longer preferential for given separations. Here's some data on absorption of plutonium, shown here, and europium, shown up here, with mesoporous carbon. So this isn't even as far as an exchange site. You can think of the mesoporous carbon as primarily affecting through cavities. Not a lot of selectivity in terms of functional group interactions with a given metal ion. And as you can see, there tends to be differences shown here with concentrations and time that it takes to reach a given plateau. Here for 10 micromole, this plateau time is on the order of tens of minutes for the functionalized mesoporous carbon, and the non-functionalized, absorption occurs around, it reaches a plateau around 100 minutes for the europium. And for the plutonium, it's a little bit faster, tetravalent versus trivalent. And then for the higher concentration, we can see that the absorption is even faster for the functionalized. Again, we seem to reach a saturation with the non-functionalized, faster with the functionalized, And with the plutonium, under these experimental conditions, again, the contact time that's measured in hours, again, that's a very long contact time, the higher concentration is much less than at the lower concentration. So again, these parameters can be varied and used to achieve some separations. One, you can achieve separation from the kinetics, but also developing kinetic parameters so that the separation occurs on a reasonable time scale. So during an ion exchange separation, we have a chromatogram that develops, which has a concentration versus elution time. As shown here, we can start off with a mixture of solutions. As it progresses down the column, we achieve a separation, and this separation is based upon the resin itself, flow rate, and conditions within the column. The elution order, as what we see here as these colors separate, is based upon the chemistry, with the strongly retained species eluting last. Now, during this experiment, we also see that as we start off, we have a relatively tight band of analyte metal ions, and as it travels through the column, we get dispersion. This dispersion is a parameter that one would like to be able to control. This zone broadening that occurs is proportional to elution time, and the separations can be enhanced by varying the experimental conditions. For instance, you may have experimental conditions where the two peaks aren't really separable. Changing experimental conditions such as flow rate, or metal ion concentration, or anion concentration can achieve a separation where peaks can be resolved and recovery of an initial mixture obtained. As we discussed during a column experiment, you can have broadening basically as the molecules undergo a random walk. You can think of this as many thousands of absorption, desorption processes that are occurring in the column during the separation. There will be an average time for each step with some variations. Your distribution will be Gaussian, so it's fundamentally similar to random errors. So the breadth of the band increases and travels down the column, as we discussed previously, because more time is needed, the more time for these average steps to have their slight variations, which result in this zone broadening. So one can see that efficient separations, you really want minimum zone broadening. So there is a trade-off between achieving a separation, so separating out the composition of what you're putting onto the column, and the zone broadening that goes on within the column. So in other words, getting most of what you're interested in out in the smallest volume possible. As we mentioned earlier, a term that one can use to evaluate a column is the number of theoretical plates on the column. And these are, as we discussed, these are fundamentally the number of basically exchange areas that occur on a column. For a given column, the number of plates, an increase in the number of plates, means that you tend to have an increase in the separation efficiency. And this can be thought of doing that separation numerous times. There's a way to determine theoretical plates on a column. So in other words, how effective a column is for a separation, from this equation here, where n is the number of theoretical plates, L is the length of the column, and H is the plate height. H, this plate height, is just described as the square of your standard deviation divided by the length. And some of the basics of theoretical plates assumes that equilibrium occurs at each plate, and from this you can model the movement of analytes down a column. You can find a theoretical plate number experimentally from the equation that's shown here, where the number of theoretical plates is equal to the length L divided by H, where L is the length of your initial to the center point of your elution peak, where you get a Gaussian distribution around the center peak, and H is equal just to the Gaussian distribution squared divided by L. Other factors there are other factors in an experiment that can impact a theoretical plate. For instance, the mobile phase velocity, a slower flow rate can increase the number of theoretical plates. However, higher mobile phases tend to have less time of the column and also less zone broadening. So these two factors need to be balanced out. What sort of zone broadening one is willing to have for having, and then the number of theoretical plates one desires for the separation. Fundamentally, one can evaluate different experimental parameters and choose the best conditions where peaks that one is interested in appear separate at the end of the column. We'll complete the discussion of ion exchange and chromatography by evaluating some data for metal ions on different columns. Here's shown some data for different elements with a strong base ion exchange resin, DOX1, as a function of nitric acid concentration. What we have plotted here is the log of the distribution coefficient from up to 10 to the fourth, or 4, since we're doing log distribution coefficient, against the molarity of nitric acid. This distribution coefficient is milliliters per gram, so that's really the milligrams or some concentration of metal ion per gram resin, divided by the milligrams or concentration of metal ion per milliliter solution. So your metal ion concentration could be moles, could be milligrams, could be activity. It doesn't matter because it cancels out. But basically what one sees is the larger this value is, larger the distribution coefficient, the greater the metal ion is retained to the resin material. And in this case, for the strong base anion exchange resin, we see that for a number of transition metals, we do not form anionic or suitable anionic species, so there's no, with nitric acid, so there's no absorption. Trivalent lanthanides, we have little as we get to the heavier lanthanides, we see no absorption. We see for the actinides that we see sorption that peaks and decreases. Again, for plutonium, plutonium-4 has strong sorption, plutonium-3 has no sorption, neptunium-4 strong sorption, neptunium-5, neptunium-6 limited, uranium-6 not as much as plutonium. So the tetravalents here seem to be strongly sorbed, whereas the tetravalents here are weakly sorbed. And this is a reasonable resin system for separating plutonium, where one could sorb plutonium onto a column with nitric acid on the order of 5 molar, high distribution, then reduction of the plutonium from the tetravalent to the trivalent on the column will cause the desorption. And again, this behavior of the trivalent plutonium is similar to the trivalent lanthanides. So we do not have sorption of those metal ions on ion exchange resins in nitric acid. Other systems will vary. Sulfuric acid, HCl, and different resins will give you some different results. Here are some elution profiles for trivalent lanthanides and actinides, separation factors relative to curium, and this is for alpha hydroxyisobutyrate. We discussed this in the previous lecture on solvent extraction. So the solution phase contains the ligand, and it's from a DOX 50 cation exchange resin. And as we see here, the elution for both the lanthanides and the actinides, we see that the lighter lanthanides, lighter actinides elute last. The heavier lanthanides, heavier actinides elute first. From the actinide and lanthanide contraction, we know that these have the smaller metal ions. So the elution here is not a charge-based separation, but an anion exchange, or excuse me, an ion exchange based separation. We can also see that the separation factor relative to curium being 1. So if we look at where curium would live right over here for the actinides, separation factor of 1, we see that we can determine that there is differences in the behavior of the lanthanides and the actinides with this system. And again, this is an example of a size-based separation. An example of lanthanide actinide separation is shown here. This is for behavior of trivalent lanthanides and actinides in a TRUEX anion exchange resin, where the solution is either 10 molar lithium chloride, the solid line, or 2 molar ammonium thiocyanate, which is the dashed line. This data up here is for the actinides. This data down here is for the lanthanides. And the striking information that's shown here is that one gets different values in the distribution volume. This distribution volume is concentration per milliliter resin divided by concentration milliliter solution. Larger number means more metal ion on the resin system. This system's of interest because not only can you achieve separation between the actinides, the trivalent actinides with this system, you can also achieve separation of the trivalent actinides from the trivalent lanthanides. And this system has been used for the separation of trivalent americium from curium. We'll discuss that in a little bit more detail. Another system which demonstrates a separation amongst the actinides is shown here. Diphonics resin from nitric acid solutions. This is again a distribution coefficient, milliliters per gram. Again, rather large numbers, 10 to the 5th, 10 to the 6th. And we see as the nitric acid concentration increases, the distribution of the metal ions tends to decrease, the thorium, uranium, americium rapidly decreasing. The tetravalents increase, reach a maximum, and then begin decreasing. And then the lowest distribution is for the trivalents at the higher nitric acid concentration. So again, separations from this system can be achieved through changes in oxidation state, whereas the previous system shown here with the TRUEX is primarily through size separation. Volatility is also a separation route that's used in the treatment of spent nuclear fuel. One simple method is something called the AIROX method. You may also see this as the DUPEC. There's some references to these methods. And fundamentally, one takes some spent uranium oxide fuel, oxidizes it to UO3. If you heat the UO2 at 400-600 degrees in an oxygen-containing atmosphere, normal atmosphere, you'll get a volume increase as it goes from UO2 to U3O8. This exposes more of the grains to the surface. Any volatile fission products will be removed. There is some discrepancy in the literature about how much of the metal ions or the fission products are removed, but some cesium, very high amounts, ruthenium, high amounts, tellurium, relatively high amounts, and then some discrepancies for other elements. The U3O8 can be treated with hydrogen. This causes a reduction back to UO2. This way, the oxide material can be treated, the size can be changed, the exposure of the surface of the particles to the surface can be increased. You can also end with UO2 at the end, and this UO2 can be reformed into fuel. And of course, during this process, noble gases, in addition to the elements that are listed here, are released: krypton, xenon, and also there's iodine removal. And as we stated, there are some discrepancies within the literature on this process. Similar to the AIROX treatment of oxide fuel, metallic fuel can also be treated and volatility can be used to separate out elements. Heating a system, obviously one would remove the noble gases readily. You can apply a vacuum and pull off some elements such as iodine. You can also use this as a zone refining technique. So if one were to heat up some spent uranium metal fuel to the point where uranium melted, these elements below uranium would be able to melt, would be able to form different phases in the fuel than those phases that do not melt, and achieve a separation that way. One could change the temperature and try to selectively remove, through a zone refining process, different metal ions from the fuel based upon their melting points. Some data is needed, and one would also have to consider the formation of solid solutions and intermetallics within the fuel. This would change the overall behavior, so it wouldn't act completely as just pure elements, but as mixtures of elements. Some reactions with additive ligands can drive volatility. An example is with using CO2 under oxidizing conditions. Nearly 70% of the lanthanides can be removed in some experiments by treating oxide fuel under CO2 up to about 1,000 degrees. Some of this work is attributed to the presence of rhodium as a catalyst, or rhodium metal, in spent nuclear fuel, driving this. This work is still at a fairly early phase. The volatile species have not been identified. Studies have shown that you get near complete removal of silver, cesium, and molybdenum from this process. Some of the data is shown below for rate constants for the volatilization by carbon dioxide as a function of temperature. Carbonyl is also another potential reactive ligand for separations, particularly with metals. An example is with the Mohn process, where nickel is treated with carbon monoxide, forms nickel carbonyls. Between 60 and 80 degrees, these compounds are volatile. Heated up to 180 degrees, the compound decomposes back into pure nickel and carbon monoxide. As an example, this can be used with metallic fuel for some separations with molybdenum. Molybdenum carbonyl can be formed. It's a volatile compound. There's no evidence of uranium and plutonium carbonyl from direct interactions of carbon monoxide with the metal. Group 1 and 2 elements, they form carbonyls with metals at very low temperatures. There seems to be no evidence of zirconium carbonyls. Lanthanide carbonyls have been observed from laser ablation studies, and volatile species have been formed, but it's unclear whether or not these compounds would form the lanthanide that is formed from the metals with the direct carbonyls. And as an example with molybdenum, other metals such as technetium, ruthenium, rhodium could form directly from the carbonyls. Halides are another example of a reactive ligand that can be used in separations. An example from industry comes from the Van Arkel process for obtaining pure zirconium. Elemental zirconium and iodide are reacted at 200 degrees. They form the zirconium tetraiodide. This metal is converted to this compound is volatile, so this conversion separates the zirconium from other materials that may be with it, thereby purifying it. And then upon decomposition, the zirconium is reduced to the metal, and the iodine gets returned back to its elemental form. So one can recover zirconium metal from this route. As you can imagine, for zirconium, one can use this as part of the fuel cycle. Fluorination of spent fuel has been proposed with uranium dioxide, plutonium dioxide, and fission product oxides that have gone under examination. Uranium can be produced as the hexafluoride with a boron fluoride fluorinating agent. So you can imagine that this, we know from the nuclear fuel cycle, is a volatile compound, so separation of that can occur. The plutonium can also be volatilized as the hexafluoride. Most fission products that form the fluorides volatilize at higher temperatures than the uranium or plutonium, so one can have a preferential distillation for the purification of the actinides from the fission products. And chlorination has also been examined, and trends are similar to the fluoride systems. Details on some of these fluorination processes are listed here. Some routes for forming actinide halides are shown below. One route, you have an exchange of fluorine with chlorine using aluminum chloride as the chlorinating agent, and you make the uranium hexachloride. In this route, the uranium fluorides can be prepared by UO2 reaction with ammonia bifluoride, or by heating metals with iodine you can form actinide triiodides. Melting points for the different actinide fluorides, hexafluorides, tetrafluorides, and uranium species are shown here, with the variations shown for the different actinides. One could use this as a route for obtaining separations, and the key being that the hexafluorides show the lowest melting point. Other trends for halides: group 1 elements produced from carbonate or hydroxide with an acid. They can also be made by metal reactions, and the melting point trends for the group 1 elements are listed here. So for fluorides greater than chlorides, bromides, and then the iodides for the melting points. Group 2 can also, trends are very similar to the group 1s, and a range of melting points are shown here, from strontium diiodide at around 500 to strontium difluoride at close to 1500, so about 1,000 degrees difference between those halide species. Again, for the lanthanides, the fluorides tend to be over 1200 degrees C for the melting point, and 600 to 800 degrees for the other halides. So we see this trend in halide behavior continue. An example of volatility-based separation with the halides is shown here for technetium. In sealed quartz tubes, technetium with elemental iodine and bromine are placed in a tube furnace, reacted at 400 degrees for 6 hours. Before the reaction, we can certainly see that this orange-red bromine color is evident in the sealed glass tube. Afterwards, that color is gone because the bromine has reacted, whereas the iodine shows very little reaction. The other thing that isn't as noticeable in this figure, but is shown here, that in the cooler part of the tube, you have the condensation of technetium bromide species. The starting material was here as elemental technetium, and on the formation of the bromide species, it migrated down to the end of the tube. This can be used as a process for separations. A final example of a separation process with a reactive ligand is shown here with hexafluoroacetylacetonate. These are known for forming high volatile species, and the synthesis of the compounds can be fairly straightforward, where the metal ion sits right here on the ligand. These can be solvent-free compounds. So in other words, the ligand is liquid phase. It can be directly reacted with the metal ions. Solvent can also be involved to help tune a reaction. The literature has shown the separation of uranium from lead with selective formation of the uranium. This can be extended. Work can be explored within the fuel cycle. There's some work that has been done, but not a great deal. And initial studies performed in our program with the actinides, lanthanides, and fission elements are ongoing. Some of the initial results have shown that group 1 and group 2 fission elements can form these hfac compounds readily and achieve separations.
This concludes the second part of the lecture on separations, where we reviewed ion exchange and volatility separations. When you've completed this section, please move to the third lecture, which covers electrochemistry-based separations.